Modern artificial intelligence often presents itself as a series of high-speed predictions. We see the final output, but the logic that generated the answer remains hidden behind layers of opaque architecture. This lack of visibility makes the system appear to function through magic. It creates the impression that internal reasoning is accessible only to those with deep technical expertise. First principles thinking dismantles this complexity by stripping away the jargon. It requires us to reconstruct the system using only the most basic, verifiable truths. Systematic reasoning begins with the simple act of noticing a pattern and naming it. This initial human observation provides the starting point for every model we build today. To understand a modern machine, we must follow the thread from that first observation through the mathematical layers that allow a system to detect, learn, and act. The transition from observation to intelligence starts with measurement. We take a real-world state, like crop yields or study habits, and record it as a numerical unit. Combining different types of measurements creates a coordinate. This localizes a piece of information, giving it a specific place within a broader dataset. This process maps real-world objects into mathematical arrays called vectors. Numbers describe the attributes of a car or the meaning of a word, placing them in a structured space. Within this space, the system uses the dot product to compute alignment. By multiplying matching components, the machine generates a score that determines how closely two vectors relate to one another. This geometry allows machines to identify clusters and relationships that are not visible to the eye. It turns a collection of points into a clear structure. Pattern detection relies on this spatial organization. Before a machine can assign meaning, it must first establish the mathematical relationships between the points. While humans can spot simple patterns, our brains cannot manually calculate the billions of spatial relationships required for a modern AI system. We automate this task using an algorithm, a sequence of logical steps that receives an input, processes it, produces a result, and checks for accuracy. An algorithm is human intuition made operational. It takes the gut-level way a person recognizes a relationship and encodes it into a set of repeatable rules that a machine can execute. Using a first principles lens means checking these rules against the original problem. We must ensure the steps transform the data in a way that serves the human purpose. Organizing thinking into exact sequences enables machine speed to follow the path of human reasoning. Curious intelligence advances when we allow the machine to correct itself. It makes a prediction, compares it to the desired outcome, and notices the difference. This measurable distance between the guess and the actual evidence is called loss. It provides the specific signal the machine needs to change. Gradient descent identifies the direction of the error, adjusting internal parameters to bring the next prediction closer to the target. Learning is the repeated application of this adjustment. Across millions of examples, the machine refines its parameters until the loss is minimized. This mechanical cycle reflects the human habit of measuring a mistake and using that evidence to guide the next attempt. Modern models achieve high performance by scaling these operations. Larger networks have the capacity to learn from vast datasets, creating richer representations of complex patterns. However, the ability to recognize statistical patterns is distinct from the ability to understand them. Machines process vectors and gradients, but they do not comprehend the context, values, or human consequences that defined our world. A system without meaning cannot register when the underlying reality has changed. It continues to follow its learned patterns even when the logic no longer applies to the situation. Scaling intelligence without meaning accelerates the frequency and efficiency of high-speed errors. Managing these systems requires both analytical reasoning and emotional awareness. This alignment provides the structure needed to govern how a model interacts with the world. The fragmented disciplines of modern AI, from data quality to agentic memory, actually form one single navigable map. When a builder understands these layers, a failed output or a new term is no longer noise. It has a specific placement on the map where it can be inspected, questioned, and repaired. This placement is what allows for responsible adoption. It gives the human in the loop the ability to see exactly where a decision was formed and who is accountable for it. Understanding the first principles of the system turns a passive user into an architect. You gain the clarity needed to navigate the technology and judgment required to carry it forward.